So this is a section now, number 4. I'm going to talk to you about the scattering Q and a little bit about the Zimm equation as opposed to the Debye equation for the light scattering. Okay, but the focus of this one is a scattering Q, how scattering Q is being defined. And the scattering Q is related to essentially theta, the scattering angle. Okay, so when the light scattering actually in principle should be depending on both concentration and the scattering angle. Okay, and then you'll have give rise to the equation called the Zimm equation. Here I give an example of high molecular weight polymer. What I mean by that is a large RG. Polymer with a large radius of gyration, then you can use the one that is Zimm equation. So, if you refresh your memory, the Debye equation was sufficient enough for us to measure the characterized weight average molecular weight and second barrier constant. What's missing here is radius of gyration, right? So in this case, is when the radius of gyration has not been measured, and if you look at the Debye equation, actually the only thing that you are using it is a concentration term, right? So I guess you can speculate that the scattering angle dependence, if there isn't any, give a rise to the radius of gyration measurement. That is a Zimm equation that is going to be shown up here. So I'm going to write a Zimm equation a few times, but let me write it here one more time. So light scattering experiment or equation prefers to write Kc over R theta. That is a unit of 1 over molecular weight. And the Zimm equation follows the same method. But now 1 over molecular weight is actually has to be multiplied by 1 plus 1/3 Q square RG square plus 2BC. Okay, so you have this sort of the quote-unquote the correction term or extra term when compared to the Debye equation. Now I need to talk to you about what do you mean by Q, and this is once again Q came from the scattering angle theta here. Okay, so let me explain the scenario. So the scattering Q, okay, should be understood in the same scenario. So I have a sample here, and I'm shining the light, and that's I guess an incident light. So this is an incident light, so Ki. Okay, and then there's a scatter light. So this is a Ks. And if they go through straight, and this is a scattering angle theta. So the scattering angle is a visual way that you can kind of understand this. And then what I can visualize here is an oscillation of electric field, the wave vector, the wavelength of the light is lambda I, right? The incident light. And we are assuming the elastic scattering with and the same colors of light will be scattered, and that's the lambda S. And elastic scattering is assumed here. So therefore, incident light and scatter light has the same wavelengths. So that's let's just call it as a lambda. Okay, and this is for the Rayleigh scattering. Elastic scattering is Rayleigh scattering. Okay, and you remember the inelastic scattering, you can look at for the Raman scattering. And so, for example, if you shine the green light, you will see some non-green color light is coming out. That is a Raman scattering. We call inelastic scattering. Wavelengths of the scatter light is not the same as the wavelengths of the incident light, and so sometimes we call anti-Stokes and Stokes shifts, and that's how you probably heard about in your micro PCAM class before. So we are talking about the elastic scattering here, and then now I am going to define the wave vector K. And here we are particularly interested in the magnitude of the wave vector, which is a magnitude of the wave vector. We can just simply call K. And then the K is essentially 2 pi over lambda, is whether it's an incident light or the scatter light that we are seeing here. Okay? And then we also can define this one as a 2 pi over n, and lambda naught. Lambda naught is essentially wavelengths in vacuum, and n is refractive index of medium. Okay, solvent or polymer solution, they are not so different, so it's you can just use that. But here is a refractive index of the solvent is much more easy to find out, so you can use that number. Okay, so this is how this wave of the light passing through, and then I am going to use some geometrical argument to actually relate it to theta. Okay, this is a scattering theta into something called a Q. Okay, scattering Q. And how I'm going to do it is, let me draw the new schematic diagram. So here I am going to just draw the same scenario, and then so this is a wave vector that has the same length. Their length K is essentially 2 pi over lambda has been defined, and then this is a extension of the transmittance line. That is a theta that is shown up here. Okay, and then what I'm going to do here is I am going to move this scatter light. Okay, this is moving together. I am going to move this scatter light to this way. See this? So if I do that, and then I'm just moving the light to the for the easiness of the geometrical consideration. So so what I did is I'm going to rewrite. I mean, this is essentially this is a K. This is a K, and this is a K. Same incident, scattering, and this is the same for what I call the same because their wavelength is the same. For now, I'm differentiating, but I'm going to move this arrow to the other side. So now this arrow stays here, and this arrow like this. They have the same length of the light, and this length is essentially K. That length is the same as a K. Let me just say that, and that's a theta. Okay. And then I'm going to define a new vector, and this is a vector. Okay, so this is a vector, and that's actually we call the scattering Q vector. Okay, so for now, let me just keep it the way it is. Okay, these are all the vector representation. So it is okay. The light wave can go this way, or they can take the scattering vectors, and if you add a correction term, which is a scattering Q, and then we'll get the same answer. So therefore, I have given you here, Q is essentially incident wave vector minus scattering wave vector. So this is a scattering, how the Q is being defined. And now you start to see this, the Q versus theta is somewhat related. And what people are really interested in scattering Q is the Q. It is a magnitude of the scattering vector Q. Okay, so this is something that essentially the length of this the red line shown up here. Okay, that's essentially the Q. So I am going to draw this one more time. Okay, so this is a triangle drawing here. The length here is okay. The length here is okay, and the length here is a Q. Okay, and then this is a scattering angle, the theta, because that's a geometrical argument. And then what I can do here is I can draw the little dotted line at the perpendicular angle to do this. Okay, and then I am going to define this as a length called, let's say, x. Okay, so from this argument, you can say the length of the scattering vector Q, which is a Q itself, is 2 times an x. Right? So that's I can do that because that's a symmetric on both sides. So this is the same as an x on the other side as well. And then I am going to draw the new right angle triangle. Is defined by this. So this is a right angle. I know this from the K, and this angle is theta over 2, and this length is an x. Okay, so can you see this? So this is the triangle here. That is the same triangle that I shaded in here. Okay? So this is a half of the scattering angle, and then we can establish this relationship. So what am I learned here is sine theta over 2, scattering angle, half scattering angle to the sinusoidal function is x over k. So that's the one. So therefore, I can say x is k times sine theta over 2. And then I can plug that numbers here, right? So finally, I got this form. Q is 2k sine theta over 2. And what did I learn about the k? That's a 2 pi over lambda, or 2 pi n over lambda naught. And everything is an intrinsic property of the system. So then I can use this this data to plug it in. So therefore, I finally got Q is 4 pi n divided by lambda naught times sine theta over 2. Okay, so this is a scattering Q equation that we were able to figure it out. So this is a scattering Q, and that's actually people just call it scattering Q. And this is related to, as you can see, the scattering angle, okay, the theta. But there is the scattering Q is much more well accepted term because you can be used not only for light scattering, but also can be used for X-ray scattering, and also people are using for neutron scattering. Anything that the scattering related one. This is a universal term that people are using instead of scattering angle. And it has a very important consideration. Can you look at the unit of scattering Q? Okay, Q has a unit of 1 over length scale. This is a very important concept for you to know, okay? Because when you look at that, the wavelengths of the light has a unit of the length, so everything else do not have a unit, so it is have a 1 over length scale. So therefore, you can have a very kind of this is a conceptual piece, concept. When you change your angle, that means change Q. Changing Q means changing the observation length scale. So this is a good way for us to kind of argue that when you're changing the scattering angle, we are naturally theta is related to Q. Q is related to the 1 over length scale, which is related to the length scale. And what is the intrinsic length scale for the polymer? That is what is called the radius of gyration, right? So that's sort of the conceptual flow, how angle changes related to the length scale changes, and that's why I spent quite a time for explain this the Q, and that's quite universally important for you to understand that. And then, as I promised, if you going back to our original kind of plan, I'm going to talk about the Zimm equation in a brief way. So let me kind of elaborate on what I have said so far onto the Q. Okay. So number 2 here is a Zimm equation, and I want to talk to you about this. Okay, so like I said, the Q is 1 over length scale. And so if you have something like intrinsic length scale to the polymer with a radius of gyration, there will be something like unit less, right? So this is something that you can consider this one to be the case that and people can use. And this is how exactly the Zimm equation use this in their notation. So the Kc over R theta, that's 1 over molecular weight unit on the light scattering experiment, and then the is 1 over molecular weight, and the Zimm equation is essentially 1/3 Q RG square. Okay, so that's the term plus 2BC. Okay, so if I take this term out, that will be what do you call? This is a Debye equation, changing the concentration and measuring the Kc value, Kc over R theta. And you can get MW and the second Burial constant. But now Zimm equation also tell you that so what I just said here is in the limit when Q value goes to 0, which means the theta values goes to 0, at the 0 angle limit, this equation, the Zimm equation, this is a Zimm equation, by the way. Zimm equation here. And what you guys need to do is this heavy equation is nothing but this factor is multiply onto what is originally known as Debye equation. So this Zimm equation complex form is reduced to Debye equation for light scattering. Okay, and so that we can get that information from here. We can get certainly concentration versus the scatter light intensity relationship gives MW and the second Burial constant. So I can calculate that. But now in the limit of concentration goes to 0, so you can change the concentration and the scattering angle. In the limit of concentration goes to 0, this is Zimm equation now. Is now reduced to a new form, which is a Kc over r theta is 1 over m 1 plus 1/3 q square rg square. Okay, so this is one of the components now you are seeing here. In this, at the limit of concentration goes to 0, and you put your plot data to the q square as your x-axis, and then this is a y-axis. You naturally can find out this term, radius of gyration can be calculated, and the 1 over m can be calculated. So this in this limit, you can calculate now 1 over mw, and the radius of gyration can be calculated. So that's the case that where the power of the Zimm equation is much more general term, but it's also kind of loaded, quite long equation. Sometimes people has not an easier way to figure out. You know, most of my polymer chemist friends, they just know light scattering of polymer is a kind of magic bullet that you guys can calculate. Weight average molecular weight, solving quality, second barrier constant, and even the size of radius of gyration. But that is actually in the limit of certain approximation. Polymer chain has to be large enough, and then we can calculate those even RG values. But when the RG is very, very small, then it's actually experimentally it's not easy to characterize a RG value of the polymer chain.